Have you ever seen a picture that looks so real you feel like you could reach out and touch it? That's the magic of a hologram. A hologram isn't just a flat photograph, it's a special kind of recording that captures a whole scene in 3 dimensions. Think about a regular photo of a toy car. You can only see it from one angle, right? It's just a single snapshot in time. A hologram, however, is more like looking through a window at the actual toy car. If you move your head from side to side while looking at the hologram, you can see around the object, just as if it were really there. It captures a sense of depth and perspective that a normal picture simply can't. This incredible idea came from a scientist named Denis Gabor, way back in 1947. He was actually trying to make better microscopes, but his work led to a groundbreaking discovery about how to record light itself. For his invention, which he called holography, he later won the Nobel Prize in physics. His discovery was a huge leap forward because it found a way to record not just the brightness of light, but also its direction and phase, the hidden information that our eyes use to see in 3 dimensions. At the time, he didn't have the right tools to make it practical. It was like he had written the recipe for a fantastic cake, but didn't have an oven to bake it in yet. The secret ingredient Gabor was missing was the laser, which was invented years later. Lasers produce a very special kind of light that is pure and organized, which is perfect for making holograms. Unlike the jumbled light from a regular light bulb, laser light travels in a neat, orderly wave. This orderliness is what allows us to record the incredibly detailed patterns needed to create a 3-dimensional image. So, while a photograph captures a simple shadow of an object, a hologram captures the light bouncing off the object from all different directions, storing it all on a single piece of film for us to view later. So, let's consider this. A photograph is like a drawing of a mountain. It shows you the shape, but it's flat. A hologram is like a tiny, perfect model of that mountain, preserved under glass. You can look at it from the left, from the right, and get a true sense of its shape and form. This ability to record and reconstruct the entire light field of an object is what makes holography so different and so amazing. It's not an illusion in the way a magic trick is, it's a true scientific reconstruction of light, frozen in time and space for us to explore. It's science. So, how do we actually make one of these amazing 3-dimensional pictures? The process starts with a laser. We take a single laser beam and use a special mirror called a beam splitter to divide it into 2 separate beams. Think of it like a garden hose spraying water, and you use your thumb to split the stream in 2. One of these beams is called the object beam. We aim this beam so that it shines directly onto the object we want to record. Let's say a small toy apple. The light from the object beam bounces off the apple in all directions, carrying the information about its shape, size, and texture. The second beam is called the reference beam. This beam doesn't touch the object at all. Instead, we aim it directly at our special holographic film. At the same time, the light from the object beam, the one that bounced off our apple, also travels toward that same piece of film. When these 2 laser beams, the reference beam and the object beam, meet at the film, something incredible happens. They interfere with each other. Where the waves of light match up, they get brighter. Where they don't, they cancel each other out. This creates an incredibly complex microscopic pattern of light and dark fringes all over the film. This interference pattern is the heart of the hologram. It might look like a meaningless blurry mess to our naked eyes, but it contains all the information about the 3-dimensional shape of our apple. Every tiny swirl and line in the pattern is a code that describes how the light looked when it bounced off the object. The process is extremely sensitive. Even the tiniest vibration, like someone walking in the next room or a quiet sound, can blur the pattern and ruin the recording. That's why holograms are made on very sturdy tables in very quiet, dark rooms. The whole setup must be perfectly still while the film is exposed. Once the film has been exposed to this interference pattern, it is developed much like old-fashioned camera film. What you're left with is not a picture of an apple, but a permanent record of that complicated light pattern. You can hold the developed film up to the light, and it will just look like a foggy piece of plastic. The apple is nowhere to be seen. But the information is all there, stored in those microscopic squiggles and lines. The magic isn't in what you see on the film itself, but in what that film can do when you shine the right kind of light on it again. Now, we have our developed holographic film, which looks like a smoky gray square. How do we get our three-dimensional apple to appear? This is the reconstruction step, and it's where the science really feels like magic. To bring the image back, we take that same holographic film and shine a laser on it. This laser should be the same type as the original reference beam we used to create the hologram, hitting the film from the same angle. As the laser light passes through the film, it interacts with the microscopic interference pattern we recorded earlier. The pattern on the film acts like an incredibly complicated filter or a super advanced diffraction grating. It bends and shapes the laser light passing through it. As the light is diffracted by all those tiny recorded fringes, it gets reorganized into a new shape. The pattern on the film essentially unscrambles the light, forcing it to travel along the exact same paths it took when it first bounced off the original apple. The light that comes out the other side is a perfect recreation of the light waves from the original scene. It's a light-based echo of the object. When you look through the film, your brain interprets these reconstructed light waves exactly as it would if the real apple were still sitting there. You see a three-dimensional image of the apple, floating in space behind the film. It has depth, it has parallax, the effect where things look different from different angles, and it looks completely solid. You can move your head up and down or left and right, and your view of the holographic apple changes, revealing different sides of it. This is what makes it feel so real and three-dimensional, just like looking through a window. One of the most mind-bending properties of a hologram is that the entire image is stored everywhere on the film. If you were to take your holographic plate of the apple and smash it into tiny pieces, you could pick up any single piece, shine a laser on it, and you would still see the entire apple. Your view would be more limited, like looking through a smaller window, but the whole scene would still be there. This is because during the recording, every point on the film captured light coming from every point on the object. The information is distributed across the entire surface, making holograms remarkably robust. Holograms are more than just a cool science experiment. They have found their way into many parts of our everyday lives. One of the most visible uses is for security. Have you ever noticed that shiny silver square or dove on your credit card or driver's license? That's a type of hologram. These are very difficult and expensive to copy, which makes them great for preventing forgeries. They are a simple, effective way to prove that an item is authentic. You'll also find them on concert tickets, banknotes, and high-quality product packaging for the very same reason. It's a high-tech security guard you can fit in your pocket. Beyond security, holography is a powerful tool for scientists and engineers. One amazing technique is called holographic interferometry. Scientists can make a hologram of an object, like a machine part or an airplane wing, and then superimpose that holographic image over the real object. If the real object is then put under stress, like being heated or pushed, any tiny changes in its shape, even changes smaller than the width of a human hair, will show up as a pattern of dark and light bands. This allows engineers to find microscopic flaws before they become big problems. It's like giving them X-ray vision for tiny structural changes. Holography has also opened up a whole new world for artists. Artists can use lasers and film to create stunning sculptures made entirely of light. These holographic artworks can show objects that change, move, or seem to float in mid-air, creating mesmerizing visual experiences that would be impossible to make with physical materials like clay or paint. These displays push the boundaries of what we consider art, blending creativity with cutting-edge optical physics. They allow artists to paint and sculpt not with pigment, but with the very essence of light itself, creating pieces that seem to defy reality. Finally, holograms hold incredible promise for data storage. Because a hologram can store a massive amount of information in the three-dimensional structure of its recording medium, scientists are developing holographic memory systems. A single holographic disc, about the size of a DVD, could potentially hold terabytes of data. That's equivalent to thousands of movies. In summary, holograms are special because they do something no other technology can. They freeze and reconstruct light itself. From protecting our money to storing vast libraries of information and creating breathtaking art, the science of holography continues to unlock a magical, three-dimensional world. It's a beautiful example of how curiosity can lead to incredible discoveries.